Hi everyone. Today I'm going to talk about some of our recent work on combinatorial Bernoulli factories. This is joint work with Rod Niazada and Renato Paisaleme. So I'm going to start with some puzzles about coins. So all these puzzles take the following form. I'll give you a coin with some unknown probability p, and I'll ask you to exactly sample a Bernoulli random variable with some probability. For example, if I ask you to exactly sample a Bernoulli random variable with probability p squared, one thing you do, even if you don't know p, is flip your coin twice. If you see two heads, return 1. If you see anything else, return 0. And if you do this, you'll return 1 with probability exactly p squared. But now, instead of asking you to return a Bernoulli random variable with probability p squared, I might ask you to return a Bernoulli random variable with probability 1/2. This is a famous puzzle due to von Neumann. A random variable with probability e to the p minus 1, or a random variable with probability squared p. So I won't explain how to do this, but the reason, you can think about it yourself, but the reason I bring it up is because this problem, these types of puzzles are exactly what Bernoulli factories are. So the Bernoulli factory problem is the following. Given a coin with some unknown probability p, and a function f of p that maps the interval 0, 1 to the interval 0, 1, can you exactly sample a Bernoulli random variable with probability f of p? So this problem is pretty well understood. There's a famous result by Keenan O'Brien that there exists a Bernoulli factory for a function f of p if either f is constant or f of p is continuous and satisfies some inequality. We'll discuss what this inequality says in a little bit. But the important thing is to understand is that this is pretty well understood. And these Bernoulli factories have applications in a wide variety of areas. They have applications in mechanism design, machine learning, statistics. They're part of like a richer field known as exact sampling, where you want to sample from some distribution exactly. In this case, you want to sample from some distribution exactly without even knowing sort of the input that this distribution depends on, this hidden number p. So let me tell you some other sampling problems, some other problems about coins. So the first problem is sampling subsets. And these will all be similar to Bernoulli factories, but instead of having just one coin with unknown probability p, I'll give you several coins with unknown probability p. So in this problem, you have n coins with some unknown probabilities p1, p2 through pn. You're guaranteed that the sum of the pi's is equal to k, for some integer k that you know, say like 5 or something. And your goal is to sample a subset of the integers from 1 through n that has size exactly k, and so that the probability you include I in your set is exactly p sub I. Right? So in some sense, you're given sort of the marginal probabilities that each element is in the set, and, well, you're not given them directly, you're given access to them through flipping a coin with some unknown probability, and from this you want to be able to sample a subset with these marginals. Here's another problem of this flavor. You have n squared coins with some unknown probabilities pij, and you're guaranteed that these pij form a doubly stochastic matrix. So if you put them into an n by n matrix, every row sums to 1 and every column sums to 1. And your goal is to sample a permutation from n to n, or you can think of it as a matching from n to n, such that the probability that I is matched to j is exactly equal to p sub ij. Alright? It's not even maybe a priori clear why you can do this, but even if you knew the pij's, but it turns out you can. And finally, let me tell you one last problem about sampling paths in a directed acyclic graph. So in this case, you're given some directed acyclic graph G with E edges. And you're given a source vertex S and a target vertex T. And your coins in this case are given one coin per directed edge in this graph. And you're guaranteed that the probabilities of these coins, if you view them as weights, form a valid flow of weight 1 from S to T. So for example, you see below, this is a valid flow of weight 1 from S to T. There's a flow of 1 leaving S, a flow of 1 entering T, and every other vertex, the sum of the weights of the incoming edges is equal to the sum of the weights of the outgoing edges. And your task here is to sample a directed path from S to T, such that the probability that an edge is in the path is exactly the weight, is the probability of the coin corresponding to that edge. So again, you're given some sort of marginals, you're given the marginals associated to edges, and you want to sample a path that satisfies these marginals. Great, so what do these three problems have in common? So one thing they have in common is that they're all sort of multivariate Bernoulli factories. They all involve flipping many coins. But in fact, they're more structured than that. They all fall under this framework that we call a combinatorial Bernoulli factory. So in this sort of framework, you're given some polytope P, that's a subset of the n-dimensional hypercube, 0, 1 to the n, and you're given n coins with unknown probabilities p1, p2, down to pn, which correspond to the coordinates of some point that's contained in p. All right, for example, in this triangle, you may be given, 2 coins which correspond to the x and y coordinate of this point inside this triangle. And your goal is to sample a vertex of this polytope such that the expected value of the vertex you sample is equal to p. So for example, the expected value of the x coordinate of the vertex you sample should be equal to p1, the expected value of the y coordinate you sample should be equal to p2. And it turns out that all the three problems I just mentioned fall under this framework. So for sampling subsets, you're working with the following polytope. You're working with a polytope the 0, 1 to the end, the hypercube, intersected with the hyperplane sum of xi is equal to k. And the vertices of this polytope are exactly 0, 1 vectors with exactly k1s, which correspond directly to subsets of size k. When you're sampling matchings, the set of allowable p's, as we mentioned, is exactly a set of doubly stochastic matrices. And it's known that this set is a polytope. It's known as the Birkhoff-von Neumann polytope. And the vertices of this polytope are exactly permutation matrices. So when you output a vertex, you output some permutation, and this constraint is exactly the constraint that the expected vertex is equal to the point you're given. Finally, for flows, we're looking at the flow polytope. We're looking at the set of x in the hypercube 0, 1 to the e, such that x encodes the flow of weight 1 from s to t. And the vertices in this polytope are paths in G from S to T. So there's some questions we can ask now. So one question is, which polytopes P can we construct combinatorial Bernoulli factories for? And for these polytopes, how can we construct these factories? Do we have a nice explicit construction, an efficient construction? So we will answer both these questions. In this work, we give more or less complete characterization of which polytopes admit combinatorial Bernoulli factories. There's a star here because it's a little bit less than complete for a subset of measure 0 polytopes. This will include some important polytopes, unfortunately, but it's still essentially complete. In addition, we give a simple algorithm for constructing such a Bernoulli factory whenever it's possible. And we'll also give explicit Bernoulli factories for the cases of subsets and matchings. For the case of subsets, it'll match up with something known in the statistics literature as Samford sampling. For matchings, as far as we know, this is a completely new method for exactly sampling matchings. So I'll briefly mention some prior work. So, as mentioned previously, the one-dimensional Bernoulli factory problem is pretty well understood, starting especially from the work of Keenan O'Brien that characterized exactly the functions that emit Bernoulli factories. This was followed by some work by Nasso and Perez that gives explicit constructions for sufficiently nice f, like analytic f in terms of things like term-specific polynomials. And there's been many other papers on very specific functions, specific settings, constructing Bernoulli factories for specific objects, etc. For multidimensional Bernoulli factories, relatively little is known. There's two papers of relatively related. The first is a paper that applied Bernoulli factories to mechanism design that introduced a specific multidimensional Bernoulli factory that we'll use called the Bernoulli race. We'll talk more about it later. The second is a paper by Marina et al., which demonstrates how to construct certain multivariate rational functions. And it'll be in some sense similar to what we end up doing. But other than these two works, there's very little that's sort of known about multidimensional Bernoulli factories. There's some maybe papers about specific functions, like, can you do p plus q, but nothing resembling a general theory like the theorem of Keenan O'Brien. So we can now state the main theorem of our paper, which characterizes exactly the polytopes which have combinatorial Bernoulli factories. And the main theorem is the following. So let P, contained in the d-dimensional hypercube, be a polytope. Then there exists a combinatorial Bernoulli factory for P, if and only if P is the intersection of the hypercube and an affine subspace of Rd. So in particular, you can go back and check, but the factories we mentioned, or the polytopes we mentioned for sampling paths and flows, all have this property. They all have the property that they are, you can write them as the intersection of the hypercube, 0, 1 to the n, and some affine subspace. But there's many polytopes where this is just not true. For example, this example polytope we saw earlier, this triangle inside the square, is not the intersection of, like a line or the plane with the square. And this is also not true for many other natural polytopes. For example, the spanning tree polytope does not have this form. So if you're given, coins corresponding to some point inside the spanning tree polytope, you won't be able to sample a spanning tree exactly. So the rest of this talk we structured as follows. In the first part, I'll describe a sketch of why it's necessary that P be the intersection of the hypercube and an affine subspace. Then I will roughly describe our algorithm for good polytopes, or more precisely, I'll exactly describe it, but I'll roughly describe some of the ideas that go into the analysis. And then finally, I'll show you the explicit algorithms for subsets and matchings that you get from this framework. So to begin, let's talk about the necessary conditions, why it's important that P is the intersection of the hypercube and an affine subspace. So to understand this, it's useful to understand why some functions in the one-dimensional Bernoulli factory setting are bad. And Keenan O'Brien's result shows that there are some functions where we cannot construct a Bernoulli factory. One illustrative such function is this function f of p equals the absolute value of p minus 1/2. So on the surface, you might expect to be able to construct a Bernoulli factory for it, like it's bound between 0 and 1, so all the probabilities make sense. But it turns out you can't, for a very simple reason. And the reason is as follows. So note that f of 1/2 is 0. And if you think about this, what does this mean? So a Bernoulli factory is really an algorithm which converts a sequence of coin flips, like, heads, tails, tails, heads. At some point, it has to stop reading, like, stop flipping the coin, look at the existing sequence, and output 0 or 1. So now, if there were any finite sequence of coin flips that would cause the Bernoulli factory to output 1, this would be bad, because there would be some chance we could see the sequence when the probability of heads is 1/2, and then f of 1/2 would be greater than 0. So this means that there's no finite sequence of coin flips that will cause the Bernoulli factory for f to output 1. Well, this is also bad, because if we look at some other point, any other point in this interval, like 1/3, this means that there must be some finite sequence of coin flips that causes the Bernoulli factory to output 1. Like, if no finite sequence of coin flips causes the Bernoulli factory to output 1, we'd also have f of 1/3 equals 0. But f of 1/3 is positive, and we've reached a contradiction. In general, we can sort of summarize this sort of argument into the following fact, which says that if f of x is 0 for any x inside this interval, then f of x has to be 0 for all x in this interval. And the same sort of thing holds for f of x equals 1. If f of x equals 1 for any x in this interval, f of x has to equal 1 for all x in this interval. So now let's talk about why some polytopes are bad, why we can't construct combinatorial Bernoulli factories for some polytopes. So we'll come up with a very similar looking argument. So consider a point P that would lie on the line segment connecting V1 and V2. So if P lies on this line segment, then the output of the combinatorial Bernoulli factory has to be either V1 or V2. It can't be V3, because P1 is entirely contained inside the convex cell of V1 and V2, and if you output V3 with any positive probability, it won't be contained within this line segment. Now, since this point, like any point on the interior of this line segment connecting V1 and V2, is contained within the interior of the unit square, all the components of P lie within 0 and 1, this means that no finite sequence of coin flips, like you can't say anything like getting heads, tails, heads from the first coin, and tails, tails, tails from the second coin. There can be no pairs of sequences like this which will cause the algorithm to output V3. But again, we sort of have the same issue as before, because sometimes we need to output V3. For example, if P1, P2 is this point in the middle of the triangle, we need to output V3 with some positive probability. Otherwise, we're going to output something with expectation contained in this line segment. We've reached a contradiction. So just as before, we can summarize this into a fact that looks like the fact we had before. Now it's a little bit more subtle. Now it says that the support of f of p, because f of p is a distribution over v1, v2, and v3, has to be constant on the interior of any facet of 0, 1 to the d. And by facet of 0, 1 to the d, I mean, in the square case, one facet is the entire square itself, so the interior is the interior of the square. There's 4 more facets corresponding to the edges. And then there are 4 other final facets corresponding to the vertices of the square. But in addition to looking at the facets of the square, we can also look at the facets of p. And the facets of p determine the support of f of p. For example, if you lie within the interior of the segment connecting v1 and v2, you have to output v1 with some positive probability, and you have to output v2 with some positive probability, and moreover, you have to output v3 with 0 probability. So if you combine these two facts, you can show that there has to be an assignment, a unique assignment, of facets of p to distinct facets of 0, 1 to the d. And with some work, you can show that this only happens when p is the intersection of the hypercube with an affine hyperplane. For example, it's true if it's only this line segment connecting v1 and v2, because that would be the intersection of this line with the square. So great, so this explains, at least in part, why we need p to be the intersection of an affine subspace with the hypercube. Why is it always possible to construct such factories? And what we'll do is we'll just give an explicit construction. Before we do that, it'll be useful to distinguish 2 classes of polytopes, generic polytopes and non-generic polytopes. So, like we've just discussed, any good polytope, one where you could hope to write a Bernoulli factory for, can be written as, the hypercube intersect some affine hyperplane. Affine subspace, I should say. And we can write this as x such that ax equals b for some k by d matrix A and k-dimensional vector b. And what we'll do is we'll say that a polytope is generic if all of the vertices of p have exactly k coordinates in the open interval 0, 1. And the reason why this is generic is that if you choose sort of like a random b, you should expect this to be true. Because all vertices of p should be formed by taking, there's sort of k constraints coming from ax equals b, and d minus k constraints coming from the hypercube, like, set this coordinate to 0, this coordinate to 1, this coordinate to 0. And the remaining k coordinates will only equal 0 and 1 if a coincidence happens. So, in some sense, with probability 0. And otherwise, if p is not generic, we say it's non-generic. And like I mentioned, almost all good polytopes p are generic. But most combinatorial polytopes are actually non-generic, because they all have entirely 0, 1 vertices. So now that we've defined generic polytopes, I'll describe how to construct a combinatorial Bernoulli factory for generic polytopes. This is complete construction. It's a simple construction, although it won't be immediately obvious why it works. But it's very simple to implement. So remember that we have our polytope P at the intersection of the hypercube with some affine subspace AX equals B, and we'll let V denote the set of vertices of P. So the factory will work as follows. First, we'll pick some vertex V from V uniformly at random. Then we'll let S be the set of coordinates of V which lie between 0 and 1. So because it's a generic polytope, we know that S has size exactly K, if A has a K by D matrix. Now, for each I that's not an S, so these are the 0, 1 coordinates of V, we will sample the coin P sub I. If the sample does not equal V sub I, we'll restart, we'll go back to step 1. Otherwise, we'll continue to step 4, where now we'll look at each coordinate inside S, and we'll sample the coin P sub I twice. If the samples are 1 and 0 in that order, we'll proceed. So in other words, with probability Pi times 1 minus Pi, we'll proceed. Otherwise, we'll restart. And then finally, if we get to step 5, then with probability equal to this magnitude of the determinant of A sub S, we'll output the vertex V. So what's A sub S? So A sub S is A where we restrict the rows to the rows that are in S. And this leaves us with a K by K matrix. If we take the determinant and its absolute value, we'll get some probability between 0 and 1. Well, we can show that. And if you, with this probability, we should output V. With the remaining probability, we go back to step 1. So this is the entire factory. Like I said, it's not obvious why it works. I'll describe some of the ideas which go into it. The full proof is in the paper. So, sort of the main sort of attack we'll use is we'll show how to reduce the problem of constructing combinatorial Bernoulli factory for a polytope to designing a set of polynomials which satisfy certain combinatorial and algebraic relations. And our main tool for doing this is the tool of Bernoulli races, which is a tool that was introduced in Dugmi et al. In 2017. This was introduced for performing certain black box reductions in mechanism design, but it's an entirely Bernoulli factory related problem. We posed like the following. So in this problem, you're given n coins with unknown probabilities p1 through pn. And your goal is just to sample integer I with probability p sub I over the sum of the probabilities. Note that this sum doesn't have to equal 1. These are just any numbers in 0, 1. And there's a simple solution to this. What you can do is you can choose a uniformly random coin, choose a uniformly random number between 1 and n, flip that coin, and if heads, return the index of the coin, otherwise go to step 1. You can show that if you do this, you will return integer I with probability exactly p sub I over sum of p sub j. So, given this Bernoulli race, how can we use this construction combinatorial Bernoulli factories? And we'll do so as follows. So the idea will be that for each vertex in our set V, we will construct some polynomial q sub v of p that we can implement efficiently with a Bernoulli factory. So for example, maybe a polynomial that looks something like 1 minus p1 times p2 times p3. You can sample this by first flipping coin 1, checking if it's tails, then flipping coin 2, checking if it's heads, then flipping coin 3, checking if it's heads. And now once we have v different polynomials like this, v different polynomials q sub v of p, we'll run a Bernoulli race over these v coins with these probabilities to choose a single vertex. Okay, and by the properties of Bernoulli races, if we do this, the probability that we output vertex v will be exactly q sub v of p over the sum over all w and v of q sub w of p. And if you now look at the constraint that the expected value of the output vertex must be p, and manipulate this above expression a little bit, you can show that this reduces to sum of v times qv of p is equal to sum of p times qv of p. So this is now just a polynomial relation in p. It's actually a d-dimensional polynomial relation in p because vectors v and p belong to 0, 1 to the d. But it's a collection of polynomial relations, and our goal is just to find some polynomials q sub v of p which satisfy this relationship, but that also are efficiently implementable by Bernoulli factories. And it turns out we can do this as follows. One construction that works, and it corresponds exactly to the procedure we saw a few slides ago, is the following. We set qv of p to equal the determinant of a sub s times the product over the coordinates where vi equals 0 of 1 minus pi, times the product over the coordinates where vi equals 1 of pi, times finally the products over the coordinates vi, which are between 0 and 1, of pi times 1 minus pi. And this is implementable by exactly the procedure mentioned a few slides ago. And like in that procedure, a sub s is the submatrix of A formed by the rows where the coordinates are strictly between 0 and 1. Great. So why does this polynomial work? So I won't go through the full proof. It's mostly a lot of bookkeeping. But one very important tool which shows up in the proof is the idea of zonotope partitions. So what is a zonotope? A zonotope is a Minkowski sum of line segments. So for example, we have these 3 line segments, this blue one, this red one, this green one. If you take the Minkowski sum, you get this 6-sided like hexagon. Minkowski sum is just the set of points you can form by adding a coordinate in here and a coordinate in here and a coordinate in here, and you'll end up with some shape like this. And there's a lot of research that's been done on objects like this, on zonotopes. And one very fundamental result in the theory of zonotopes is that you can decompose a zonotope into parallelograms, or parallelepipeds in higher dimensions. So for example, in this zonotope we got by adding 3 line segments together, we can decompose into these 3 parallelograms. You notice that each pair of line segments appears in its own parallelogram. And what does this have to do with the polynomials we saw in the previous slide? So our proof involves manipulating these zonotopes generated by rows of A. And one thing you can think about is that the volume of one of these parallelepipeds is going to be the determinant of some subset of the rows of A, and it will exactly be one of these determinants of A sub S. And essentially, proving this polynomial relationship will boil down to exactly this decomposition relation, that you can decompose this zonotope into a bunch of parallelograms, each of which has volume equal to one of these determinants. So I won't say anything else about the proof, but this is the main technical idea. A lot of the rest is just algebraic manipulation of these polynomials. So finally, all the previous factories we've described have worked for generic polytopes, and for light on the polytope being generic. There's a very simple way you can convert a factory for generic polytopes into a factory for non-generic polytopes. And the idea is as follows. What you want to do is you want to perturb P slightly. Specifically, you want to add a tiny perturbation to B, if the hyperplane is x equals B, to create a generic polytope. For example, you take this non-generic polytope formed by this line segment here, and perturb it a little bit to get this generic polytope formed by this line segment. Once you have a generic polytope, you can run the Bernoulli factory for the generic polytope, outputting one of the vertices of the generic polytope. And then you can round these vertices back to the corresponding vertex of the non-generic counterpart, as long as you didn't perturb by too much, to get a factory for the original non-generic polytope. And you can show that this sort of procedure works. There is a tiny caveat, which is that sometimes the resulting factory is not guaranteed to terminate for points which have coordinates which are 0 and 1. So it sometimes only terminates for points in the open hypercube 0, 1 to the n. In contrast, for generic polytopes, it terminates for every single point in the closed hypercube 0, 1 to the n. It's an interesting open question to understand when exactly this happens. We have some partial results, but in general it's still open. All right, finally, to close off this talk, I want to present 2 specific factories that we can get from previous methodology. The first will be a factory for sampling subsets of size exactly k. And the second is going to be a factory for sampling matchings, or permutations. So the first, like I said, is a factory for sampling subsets of size k. This procedure is already known, actually, in the statistics literature. It's called Samford sampling. So we recover the Samford sampling algorithm. And what it does is the following. So remember, you have a bunch of coins. They're probably sum up to k. So what you start by sampling every single coin. If it comes up heads, add its index to your set S. Now you have a set S of some number of coins. It might be fewer than k, it might be larger than k. If the number of heads was not exactly k, restart. Go back to set 1 and keep on sampling until you sample a set which is of size exactly k. Then, after you've done this, you do one more thing. You choose an element of your set uniformly at random, so one coin from your set uniformly at random, and flip that coin again. If it comes up heads, then restart. If it comes up tails on the other end, then output the set S. So the interesting thing is that, and this is common in a lot of these Bernoulli factories, is that instead of just, if you terminated right after 2, if you output S as long, if S had exactly k elements, your set would be biased. It would not have the correct marginals. You really need to do this third step to correct the marginals of S. And the same sort of thing happens for matching. So this is a factory for matchings. As far as we know, it's like a new method for exactly sampling, if you want to call them matchings or permutations. And it works as follows. So you start, as in the previous case almost, by picking a uniform random permutation pi over n, or you can think of this as a random matching in the complete bipartite graph. Now for each edge in this matching, you want to flip the coin corresponding to this edge. So this is like the p sub I pi of I coin. If you get tails, restart. If you get heads for all of these coins, you can jump to pick step 3. And what's interesting in step 3 is now we pick a uniformly random spanning tree of the complete graph k sub n. And what we'll do is we'll now orient all the edges of this complete graph, not of this complete graph, of the spanning tree towards vertex 1, and let T be the set of directed edges in this arborescence. And then finally, for each edge in this arborescence, we now flip a coin corresponding to this edge. It's not exactly p sub ij, we do p sub I pi of j. And if we get tails for any of these coins, we restart. But if we get heads for all of them, we output the matching pi. And somehow, this procedure, this set of steps between 3 and 5, where we look at not only a random permutation, but in addition to that, a random spanning tree on top of this permutation is also important to correct the marginals of pi. So that's it for this talk. I've left some open questions on this slide, and I'm happy to talk more about open questions of this work. I hope you enjoyed the talk, and thanks.